everyone, welcome back to Measure Theoretic Probability, or maybe I should say welcome in the first place because it has been so long since I've posted. I doubt any of my original viewers are still here, but we are talking about almost sure convergence for a sequence of random variables. That's what I said was coming next all those months ago, and I do want it to come next, but I have to talk about a few things first, and that is about how we can combine measurable functions into other types of measurable functions. This really should have its own video, but in the interest of moving forward and doing what I promised in this video, I'm going to try to put a little bit here and go forward. So imagine I have two measurable spaces. That's a non-empty set omega 1 with a sigma field or sigma algebra curly F1, and a non-empty set omega 2 with its own sigma field or sigma algebra curly F2. A function f taking values in omega 1 and returning values in omega 2 is said to be measurable if the inverse image under f of any sets from this sigma field pull back into sets from this sigma field. Specifically, we say that f is measurable curly f1 slash curly f2 or something like that, or something that says with respect to. But given these are our two spaces, and I'm talking about a measurable function from one to the other, I think it's pretty clear which sigma fields we're talking about. So I'm just going to say that f is a measurable function. If omega 2 is the set of real numbers, then we have a real valued function here in f. And if you have a real valued function, you can always assume that the sigma field associated with the second space is the set of Borel sets unless explicitly stated otherwise, because that's almost always what it is. So maybe you can't do that in life, but I'm going to say in here, if we're talking about a real valued function and I haven't given you a specific sigma field for curly F2, you can assume it is the Borel sets on R. Now, a random variable is usually defined in the context of a probability space, and yet it's defined to be a measurable real valued function. And the real valuedness or the measurability, none of this involves a measure. You'll notice I didn't have a mu1 and mu2 up here, or a p1 and p2. So technically, we can talk about random variables outside of a probabilistic setting. It's just equivalent to talking about measurable functions. In the beginning of today's video, before I get back to convergence of sequences of random variables, I need to show you that, for example, the sum of two measurable functions is measurable. And you might have seen this in a more general analysis course. You might have a measurable function, little f and little g, and you want to show that the sum is measurable. And if those functions, f and g, happen to be random variables, so be it. There's no difference. Because we're in a measure theoretic probability course, I thought I would maybe keep talking about random variables, but everything I do today, almost everything, will hold for any measurable functions. So if you stumbled across this video because you're struggling with a homework problem to show that the sum of measurable functions is again measurable, you can use what we're doing here, even if you don't have random variables. So x from an omega f and presumably with a probability measure p into the reals and the Borel sets is a random variable if the inverse image of Borel sets is always in f, the inverse image being under x. And we had a theorem last time, or possibly right before that, within the last two lectures, that say that a function x going from omega into r with these two spaces is a random variable if and only if the set of omegas for which x of omega is less than or equal to x is in curly f for any real number x. So one direction of this is not surprising at all, because this being the inverse image of an interval from minus infinity up to x closed on the right, this is a Borel set. The inverse images of all Borel sets, given you have a random variable, must be in f. So the forward direction is a direct consequence of the fact that this is a random variable. But we showed the other direction based on the fact that this set here generates the Borel sets. So again, the forward direction is just the definition of a measurable function, and this being a Borel set, but the backward direction is based on this kind of set generating the full class of Borel sets. And this means that there are many different kinds of sets we can put here and still have this theorem. For example, we can look at the inverse image under x of the interval closed x up to infinity. Because this is a Borel set, and if x is a random variable, we definitely know the inverse image of this must be in curly f. That is, we definitely have the forward part of this theorem. But I claim we can get the reverse of this theorem as well, using the fact that you can generate Borel sets with intervals of this form. So you just have to go back and look at that proof in the last or the previous, right before that video, and penultimate. I missed the chance to use the word penultimate, but I digress. So if the inverse image of sets like this, or even this, where x and y are real numbers with x less than y, are in F, inverse image under X, then we do have a random variable. So this means instead of checking the inverse image of Borel sets, we can check inverse images of things like this, or this, or this, or this, or many other types of sets that generate Borel sets that we talked about at the beginning of this course. So before talking about almost sure convergence for a sequence of random variables, I do need to show you that the sum of two random variables is again a random variable. This is totally equivalent to showing that the sum of two measurable functions is again a measurable function outside of the context of probability. To do this, I'm going to take some intermediate steps first. Suppose that I have a measurable space, a non-empty set omega, and a sigma field F. And suppose that x and y are random variables on this space. That means they must be real valued, and I'm talking about Borel sets for that second space. I claim that the set of omegas for which x of omega is greater than y of omega is in F. Let's show it. I'm going to start out with just rewriting this set by suppressing the omega notation just for fun, just to make sure we're comfortable going back and forth. So this set where x is greater than y is just shorthand for this set up here. And I want to rewrite this as a union of a bunch of events where I separate x and y by a real number. And if I union over all possible real numbers, I'll just get back to this set over here. Now I'm trying to make an argument that this set is an F, and hopefully I can say that this is an F, and then the union, I'm actually in trouble. I'm in trouble because sigma fields are closed only under countable unions, and the real numbers are not countable. I hate to say things without proof, but at some point I do have to stop, or I'm going to just do all of plain analysis. I claim that instead of unioning over all real numbers R, I can union over all rational numbers R. So this like bold-face Q is a set of rational numbers. And the argument here, which I'm not going to be able to go through in the interest of time, is the fact that the rational numbers are dense in the real numbers. So if you take any two real numbers, no matter how close they are, you can always find a rational number between them. That doesn't prove that the union over the reals here is the same as the union over the rationals, but it is the idea how you can only union over the rationals here and not all of the reals. So I'm going to have to leave that, and I'm sorry about that. But let's break this set up into an intersection of two sets. The event that x is greater than r is greater than y is the intersection of the event that x is greater than r and r is greater than y. Now, this set right here, that x is greater than r, this is the set of omegas for which x of omega is greater than r. And this is the inverse image under the x function of the interval open r to infinity. This is a Borel set, and because x is a random variable, this inverse image is in F. So we can say that this set here is in F. Similarly, we can argue that this set is in F. F is a sigma field, so it's closed under finite intersections for sure. So all of this is in F, and it's closed under countable unions. So this entire thing is in F. This thing is equal to this thing, and this is what we wanted to show. So we're done proving this claim that the omegas for which x of omega is greater than y of omega is in F. I could redo this proof easily with a greater than or equal to, certainly with a less than, because x and y are just two random variables, and there's no real reason to have one below the other. But I can also change this up a little bit and put equalities and several other things that we're going to use along the way. So keep that in mind. Later, I might suddenly claim that a set is an F and refer you to this proof, and it won't be this result exactly, but very, very similar. So continuing with the setup that X and Y are random variables, I'm going to take a real number A, and I claim that X plus A is still a random variable. And I don't think anyone would have trouble believing this, but how can we show this? To prove that it's a random variable, I'm going to take any X in the reals, and I'm going to consider the set of omegas for which X plus A of omega is less than or equal to X. Now this is, a sum of functions, and this literally means X of omega plus A of omega, if you will, but A of omega is like a constant. It's always A. So this can be rewritten as X of omega plus A being less than or equal to X. If I move A to the right-hand side, we're talking about the set of omegas for which X of omega is less than or equal to X minus A. But X is a fixed real number, and A was a fixed real number. X minus A is another real number. And this is the inverse image of a Borel set, A minus infinity up to X minus A inclusive. And therefore, because X is a random variable, we know this is an F. And that's what I wanted to show, because now we know that this set is an F, and we have proven that X plus A is a new random variable. One more basic one. If I take a real number A and multiply it by the random variable X, I claim that's another random variable. To prove this, I'm going to look at all the omegas for which AX of omega is less than or equal to some X, where X is any real number. This again is defined to be A times X of omega. So let's replace that. And to finish this off, to show that this is an F, we need to consider three cases for A, where A is positive, 0, or negative. They're all very similar, so I'm just going to write out the third case. If we are in the third case, where A is negative, and we move the A to the other side of this inequality in order to isolate X, we are going to flip the inequality because A is negative. So this becomes the set of omegas for which X of omega is greater than or equal to X over A, but this is a real number. And therefore, this entire set, because X is a random variable, this entire set is in F. Again, if you need to, rewrite this as the inverse image of the Borel set from X over A closed to infinity open. And the inverse image of Borel sets under random variables are always in F. So we get that this is an F, and therefore this is an F. And therefore we have shown that A times X is a random variable. So here's what I was going for. And those other things were not really just lemmas for this. I'm going to need all those results today for different things. So they were all completely worthwhile. But I want to show that if you have random variables X and Y, that X plus Y is again a random variable. I'm going to start off the same way. I'm going to look at the set of omegas for which X plus Y is less than or equal to little x, where little x is just chosen to be any real number. We want to show this is in curly F, and we're done. The first thing I'm going to do is move Y to the right side of this inequality. Now I'm looking at the set of omegas for which capital X is less than or equal to little x minus capital Y. But if you use our properties, or I don't know, the things we're in a list of things we're showing. If you use 2 and 3, namely that you can add a constant to a random variable and get another random variable, and you can multiply by a constant and get another random variable. And if you think of multiplying the random variable by the constant -1, we do know that this quantity over here is in fact another random variable. And now we're back to property 1 in the list. It's not exactly how I had it. I had a greater than, and this is less than or equal to, but we do know essentially that this is an F by property 1, or by a very similar proof to property 1. So we've shown that for any x in the reals, this set of omegas are suppressed, is in F, and that means that X plus Y is in fact a valid random variable. Actually, one more before we talk about almost sure convergence. If X is a random variable, I claim that the absolute value of X is a random variable. And I really do need to take the time to do an entire video on different operations of measurable functions that are still measurable. In fact, this is a special case of a result that says that the composition of measurable functions is still measurable, assuming all the spaces kind of line up correctly. For now, I just want to show this simple fact and not talk about composing the measurable function, that is the random variable, with the measurable function, the absolute value of x. Let's just do this one specifically, and hopefully one day I can insert a video into this series which just talks about measurable functions and all these different combinations. Okay, so I'm going to start with taking any x in the reals, and I'm going to, as usual, consider the set of omegas for which the absolute value of x of omega is less than or equal to x. Now, where we go from here depends on whether or not this real number x, which you can think of as fixed, is negative or greater than or equal to 0. If it's negative, then I'm looking at the set of omegas for which the absolute value of x of omega is less than or equal to a negative number, and that's not happening. So that set is the empty set, and the empty set is in the sigma field curly f by definition of a sigma field, so we're good here. We have shown that this set is in F as long as the little x that we're using here to define this set is negative. Let's look at the other case where this little x is greater than or equal to 0. In that case, this set can be written as a set of omegas for which negative x is less than or equal to capital X of omega is less than or equal to little x. This is just the inverse image under the random variable x function of the interval from minus x to x closed on both sides. This is a Borel set. I'm not saying that this type of set generates Borel sets. We do know that if you had like a closed x to a closed y for all x and y, those would generate the Borel sets, but not so clear and actually not true that sets restricted to this form would generate Borel sets. But it's unimportant because this is a Borel set. Whether or not it generates Borel sets, it is a Borel set, and x is a random variable. So inverse images of Borel sets, if you have a random variable, are in the sigma field. And so this is an F. And therefore, we've shown that this is an F, regardless of whether x is negative or not negative. And that's what we needed in order to show that the absolute value of x is another random variable. Back to limits of sequences of random variables. There's many ways to think about a limit of a sequence of random variables. Let's start off with a sequence of random variables, capital X1, capital X2, on up, on a common probability space consisting of a non-empty set omega, a sigma field curly f, and a probability measure p. We do need a common probability space to talk about a sequence of random variables for things to make sense. The question we had in the last video is, what does the limit as n goes to infinity of xn equaling some x mean? We know what limits for sequences of numbers mean. We have an epsilon and things get close and blah, blah, blah. But these are not numbers. They are potential wannabe numbers, and they take on different values with different chances. And it's just a little more complicated. So to show convergence for a sequence of random variables, we essentially have to bring real numbers into it somehow. One way to do that might be to talk about the limit of the expectations of these guys being the expectation of this guy. These are real numbers, and this is a real number. Another thing might be to talk about the probability that these guys are close to or far from this guy. And probabilities are real numbers, so we do know how to talk about limits like that. We will talk about these particular limits, but this is not the type of convergence I want to talk about today. I want to talk about almost sure convergence. We say that xn converges to x almost surely if the probability measure of the set of omegas for which this limit of the xn omega is equal to x of omega is 1. So this is a subset of capital omega, and the probability measure has been defined on most subsets of capital omega. So hopefully this makes sense, but we do need this set to be in curly f. Just as a reminder, I can write this in shorthand as this and sort of suppress the omegas, and we're going to do that a lot. When this happens, we say we have almost sure convergence of the xn to x, and we write xn with an arrow and an as over it to x. Another term for almost sure convergence is convergence with probability 1. And if you've had any sort of analysis where you've talked about convergence almost everywhere, it is the same thing. But in a probability context, almost everywhere becomes almost surely, because it's more like I don't know, our chances. Is this going to happen? Definitely, sometime, surely. I don't know. It's just the language we use in probability. So it's the same thing as almost everywhere at convergence. Now, I was saying for this probability to make sense, the probability measure needs to be defined on the set. So the set needs to be in the sigma field. You might say that saying something converges almost surely is going to imply that, because otherwise you don't have this, and therefore you don't have almost sure convergence. So you might say that almost sure convergence is implying that this is an F. But if you bear with me until the end of this video, I'll show you why you know that this set is in curly F. First, however, I just want to do a straight up example of almost sure convergence, like an exercise that you might find in your probabilistic measure theory homework. So I'm going to take a non-empty set omega to be the closed interval in the reals from 0 to 1. I'm going to take P to be Lebesgue measure, which is just our concept of length of intervals, because the space is 0 to 1, the total length, and therefore the total measure of this space is 1. And so this is going to be a valid probability measure. Because we're working with real numbers, I do want to use Borel sets, and I'm going to use the sigma field to be all the Borel sets generated by the real numbers between 0 and 1 inclusive. So with this, and this, I have a probability space. Let's define a sequence of random variables and see if we can't figure out something about where they're going almost surely. I'm going to define xn of omega to be 1 if omega is greater than or equal to 0 and strictly less than 2n plus 1 over 3n. For the other omegas in this interval from 0 to 1 inclusive, I'm going to define xn of omega to be 0. So there's a sequence, and I'm going to now define a limiting random variable. What do you think it's going to be? I think you know what this is going to be. If you just imagine in, the sense of convergence that you know about now, if I let n go off to infinity, this endpoint over here is going to 2/3. So I think that this sequence is going to converge to the random variable that is either 1 or 0 when omega is between 0 inclusive and 2/3 not inclusive. Let's just bring up a slide, shall we? I'm going to define another random variable x to be 1 if omega is greater than or equal to 0 or strictly less than 2/3 and 0 otherwise. I want to determine whether the xn's defined on the previous slide are converging almost surely or almost everywhere to this x. To do this, I'm just going to follow the definition. We do have many equivalent ways to show almost sure convergence coming up in the next video. But to follow the definition, I'm going to let A be the set of omegas for which this limit of these xn omegas is equal to this random variable evaluated at omega. I want to prove that the probability measure of A is 1, and that's enough to show almost sure convergence. That's the definition. As a reminder, here's the sequence, and here is what I'm calling the limiting random variable. Let's look at this number over here. There's 2n plus 1 over 3. This is converging to 2/3, and it happens to be converging down. So as n gets large, this sequence is decreasing down to 2/3. So this interval here includes numbers above 2/3 because that limit is coming down from above 2/3. And this means that we have some omegas for which xn of omega is 1, and yet x of omega is 0 because x of omega is 0 whenever you have an omega greater than 2/3. So let me try to say that again. If you have an omega greater than 2/3, it's some of your xn of omegas are going to be 1, while your x of omega is always going to be 0. So we do have a problem there, but maybe that's a problem on a set of probability measure 0. So maybe we have convergence that we want on a set of probability measure 1. Let's figure out what that set is, that A set. I'm just going to go through the cases. I'm going to start with an omega greater than or equal to 0 or less than 2/3. In this case, xn of omega is always 1. And in this case, x of omega is always 1. So the limit of these guys is this guy. I mean, we've just got a constant sequence here. And this means that we have convergence of the random variables xn to the random variable x for all points omega in the interval closed 0 to open 2/3. I'm going to skip that 2/3 for the moment If omega is greater than 2/3, then x of omega over here, we can clearly see, is 0. If omega is greater than 2/3, xn of omega might actually be 1 if n is small enough. However, when n gets large enough, the xn of omega is going to be 0. I claim that the xn omega is going to be 0 whenever n is greater than 3 omega minus 2. How did I get this? I just took this inequality here and solved for n. So this is just equivalent to this. So again, when omega is greater than 2/3, x of omega is equal to 0. When omega is greater than 2/3, especially if it's just a little bit above 2/3, x1 of omega, x2 of omega, those might be 1. But when n gets large enough, the xn omega is going to be 0. And how large is that n? N needs to be greater than 3 omega minus 2. So if you imagine the sequence of the xn's, you maybe have 1, 1, 1, 1. Eventually, you get to 0, 0, 0, 0, 0, 0. And that is converging to 0, which is what x of omega over here is when omega is greater than 2/3. So we do have convergence of the xn's to the x whenever omega is in the interval open 2/3 to closed 1. So we just have that one problem point, and it's really not that much of a problem because although we don't have convergence there, we are okay because we want convergence with probability 1 or on a set with probability measure 1. When omega equals 2/3, this xn omega is equal to 1 for every single n. And over here, when omega equals 2/3, x of omega is 0. So this is a sequence of ones, and this is 0, and this constant sequence of ones. We have a problem with the limit here. The limit of xn of 2/3 is not equal to x of 2/3. So we do not get convergence of xn omega to x of omega when omega is 2/3. However, we do get it on this set. Closed 0 to open 2/3, unioned with open 2/3 to closed 1. This is a set with Lebesgue measure 1. This is the whole interval from 0 to 1 with just a single point taken out, which is not affecting the length of that interval or the sum of these two lengths. The point 2/3 has Lebesgue measure 0. So this is the set A I was talking about when I defined A to be the set where we have convergence. Therefore, we have shown that the probability or Lebesgue measure of A is 1, and this means we have shown that xn converges almost surely to x. Again, this is the same as almost everywhere convergence if you're used to non-probability, but some measure theory and some kind of analysis course. So to wrap up today, I'm going to go back to where I first defined almost sure convergence today. And it had to do with a probability measure of a certain set being 1. We define basically a set A to be all the omegas for which the limit of the xn omega is equal to x of omega. And the probability measure of this can only be 1 if the probability measure is defined. So this needs to be in the sigma field. As I was saying earlier, if you're claiming that xn converges almost surely to x, then you're saying this has probability measure 1. So you might say, isn't it built into the definition? And I would kind of agree with your argument, but we can show this actually formally. So let's do it. To recap A, the set A in our notation where we sort of suppress or obscure the omegas, A is the set where the limit as n goes to infinity of xn equals x, where xn is the sequence of random variables and x is another random variable. But yes, this is a subset of omega. Now, if you have a point in A, then that means that for that omega in A, because this limit is equal to this, now once you plug the omegas in here, this limit equaling this is just a sequence of real numbers converging. So if omega comes out of A, this happens if and only if, for any epsilon greater than 0, we can find a non-negative integer, capital N, such that the distance between these two real numbers, xn omega and x of omega, is less than epsilon for all little n greater than or equal to capital N. That's just what it means for this limit to exist once you've plugged in a particular omega and we're talking about real numbers. So now I want to rewrite the set A In terms of intersections and unions, we are trying to show that this is an F, and if we can do that, maybe we can get to where we want to be. For all epsilon greater than 0, for all in terms of sets is an intersection. I claim, and I think it'll be clear at the end, but maybe not as I'm building it, so bear with me. The set A is going to be the intersection over all epsilon greater than 0. That's the for all epsilon. There exists a capital N. So it could be capital N equals 1. It could be capital N equals 8. I don't know. If we union over all capital N from 1 to infinity, we will pick it up. We want this event to occur for all lowercase n greater than or equal to capital N. For all is another intersection, and I want to intersect over lowercase n from capital N to infinity, and then I want this event to hold. So pause the video if you have to, take a moment to look at this and convince yourself that this set A is equivalent to this sort of description of what it means to be in the set A. I want to show that this thing is in curly F, is in the underlying sigma field, so that we have that our almost sure convergence definition, everything is nice and well defined, and the probability is on a set that is measurable and all of that. But I do have an uncountable intersection here, and that is a problem for closure under sigma fields. I am only guaranteed that if I take sets in F, the intersection of those sets are still in F for countable intersections or unions. So I need to adjust this. I need to deal with this. And this is a trick that comes up a lot in here or maybe other measure theory courses. I'm going to try to turn this into a countable union. So consider again this criteria for being in the set A. And note that for any epsilon greater than 0, we can find a positive integer k such that 1 over k is less than or equal to epsilon. That means, and this might be another one that you have to pause and think about a little bit, but we can rewrite this star expression up here, which is the criteria for inclusion in A, in terms of these integers k, or these distances 1 over k. Because if you need to be less than epsilon for all epsilon, then if I replace this with like a 1 over k, I can always take k small enough or large enough to be on both sides of epsilon, and we can get this statement to hold with a 1 over k instead of epsilon. So if omega is in A, we can say this happens if and only if for every positive integer k, there exists a capital N such that this distance is less than 1 over k for all n greater than or equal to capital N. With that, I can rewrite A as a countable intersection of a countable union of a countable intersection of sets. If this set is in F, then by countable unions and intersections, by sigma fields being closed under those, this whole thing will be in F. That's what we wanted to show. Why is this in F? The xn's are random variables. The x is presumably a random variable. I think I need to talk more about that. If I define the limit of random variables to be something else, is that a random variable? Should probably say something. I'll do that in the next video. But this is a difference of random variables, and that's a random variable because we showed at the beginning the sum, or if you multiply by -1, so a difference, the sum or difference of random variables is a random variable. Now, this is the absolute value of a random variable, and we saw today that that's also a random variable. So right here, this set is an inverse image under a more complicated random variable of the interval from, let's just cover our bases, -infinity up to epsilon open. This is a random variable. This is an inverse image under a random variable. We know that this is an F. So remember, we're talking about almost sure convergence of a sequence xn to an x. And we define A to be all the omegas on which the limit of the xn of omega is equal to x of omega. And if we have almost sure convergence, we want the probability measure of this set to be 1. And if we want to be able to take the probability measure of this set, the set does need to be in our collection of measurable sets, F. And that's what we just showed. So we're done. Okay, so I only got to one example of almost sure convergence. In the next video, I promise many more concrete examples. And then I want to talk about other ways to create random variables out of limits, like if I state that the limit of the xn is x, am I guaranteed that x is a random variable? And are there other ways to define almost sure convergence? I wouldn't say I would define them in other ways, but there's definitely equivalent criteria to our definition that you might find easier to apply in practice. So I hope to see you in the next one in like 8 more months.